I'm going to be talking to you about Commission 1, which is basically dealing with concrete structures. So my name is Jessica Sandberg. I'm a chief engineer at AtkinsRéalis. And we're going to be looking at the Commission 1. Basically, what FIB does, it splits its activities across 10 different commissions. Each of these commissions deals with a different aspect related to concrete. Commission 1 then focuses on the concrete structures themselves, and its remit is to set out what's set out on this slide here. It's particularly the key aspect of Commission 1 is to endeavour to promote practices leading to sound, economical, durable and aesthetic design with special attention to sustainable development principles. So the Commission 1 is split up into 8 different task groups. Those task groups are sort of set out on this slide here. Within that, each of the task groups has working groups, which all deal with different aspects within the different concrete areas. So within each of the working areas, the aim is to output various things from the different groups. So each individual group will be working on different aspects, and the output will generally form the basis of typically guidance, recommendations in terms of bulletins or state-of-the-art guidance documents and things like that. The ones that are coming out within the next year or so are the ones set out on this slide here. I'll be going into a little bit more detail on what we're doing in Working Group 1.1.3 for integral bridges, which currently has a document that's being drafted. So going on to the detail of Working Group 1.1.3, there's 2 of us convening in the group. There's myself and Alessandro Palermo. We have about 26 members within the Integral Bridges group from different regions of the world, 12 of which are active at the moment and actively contributing towards the state-of-the-art document that we are in the process of producing. So the current state-of-the-art document that we are looking at right now is intended to pull together Integral Bridges design approaches from the different regions in the world, and trying to take all that, pull it together and sort of highlight how we do things similarly to each other and how we do things differently. And most importantly, just capturing how we do things so that we can learn from each other and develop the best way of doing integral bridge design and share that with the bridges community at large. The main component or main sections of this document will contain sort of the definitions, general introduction, the design basis, mostly focusing around performance criteria and loads and load combinations. It will look at analysis approaches, both simple analysis approaches, and there will be some detail about more detailed source structure interaction approaches for integral bridges. And the design approaches adopted in different regions across the world. And there will also be quite a useful section, I'm hoping, on common detailing practices and case studies. Maybe going back a slide, for those of you who don't know what an integral bridge is, an integral bridge is basically a bridge that is all built in together. So you generally have the sort of foundations will be built into the abutments, and then you'll have an integral connection between the deck concrete and the abutment concrete. So this means that you essentially remove the need for complex joints and bearings within the section. And the reason that we tend to try to promote this is that it generally leads to lower whole life costs, less maintenance, less disruption to the network. So most of our clients are quite keen on using these sorts of structures because it just helps make the road networks and rail networks easier and less disruptive. So going on, I find this quite a useful slide in that it sort of highlights how different regions do things differently. We haven't quite got a full list of all countries at the moment, but I think this illustrates the general differences between some of the countries. So for instance, Finland tends to do integral bridge design between about 50 meters to 90 meter spans, with steel being limited quite a lot more than concrete bridges. There seems to be a general trend throughout a lot of parts of the world where concrete bridges are generally tend to be longer integral bridges than the steel ones. The exception to that is probably the UK, where we don't really have any limitations on the length of integral bridges depending on concrete or steel. It's just the same limits for both. Not all countries define the same limitations on when you're allowed to use integral bridges. So some define it based on movement range, and others on the total length of the bridge that you can use. And then there's also some limitations on skew. So this slide then further goes on and sort of gives a couple of other limitations for a couple of other examples. The key outlier on this is clearly the United States, where they do some very, very long integral bridges, though the length of the integral bridge tends to be state dependent. So the longest integral bridges tend to be in the central states of the US, where you've got a lot of seismic concerns. The lengths tend to be quite significantly curtailed because of concerns regarding the seismic detailing, and you can't quite develop the same length of structure when you've got the problems of the seismic design. So that also affects things. So within the definitions, this is quite an important part of the state-of-the-art document, because we have to have an agreed set of terms that we use to define the structural design. And it's taken a fair bit of work to get a set of definitions that we can all agree on, because it turns out that we all use slightly different terms and we define things in slightly different ways. Then we will have a sort of section on the general introduction and the types of integral bridges that are commonly used throughout the world, varying from full height abutments, which are shown on this diagram here. We'll also have sort of bank heights, bank seat abutments and pad abutments, which tend to have much shorter abutment heights. They tend to sit on the top of an embankment. The benefit of those is it mobilizes less soil when it expands and contracts. You also have embedded wall abutments, which tend to be contiguous pile walls, which tend to be used for top-down types of construction. Flexible support abutments, these tend to be about the types of abutments where you've got a column that goes through a manhole ring or something similar that then separates it from the soil, and that then limits the amount of earth pressure that you then mobilize behind the end of the abutment. The earth pressure being the main component of the sort of interaction between the soil and the structure itself. And then you've got semi-integral abutments, which are sort of integral bridges with bearings, but without the sort of complex joints at the surface carriageway level. There's some interesting work being done in France at the moment, where they are sort of retrofitting some of the existing structures and turning them into semi-integral bridges. So bridges that have previously had joints in the deck are being turned into semi-integral structures, which I believe is giving them a maintenance improvement on the road network that they've got. We will then have a section looking at the design basis, mainly focusing on performance criteria. This will focus on the fact that when you're doing integral bridge design, it tends to be flexibility and the stiffness of both the structure itself and the soil tends to be quite important in determining the load effects that you have, and the amount of thermal movement that you get. So the expansion of the bridge then causes the deck to move into the soil, thus mobilizing a sort of semi-plastic soil resistance that then sort of effectively mobilizes load within the abutment. So the more flexible you can make the system, the less load you have getting locked into that system, and the easier the structure then becomes to design. And the key to this section will then be how different regions address these issues of how we quantify the sort of semi-passive soil resistance, which in the UK is we refer to as the K-star soil pressure, and other regions tend to refer to it as sort of a passive soil resistance, depending on the soil movement. It all depends on which region you're in. The intention is also to look at the creep and shrinkage effects of the design of the structure and sort of highlight how that affects the design, because again, there are subtleties in how this is dealt with differently between regions, particularly how this is dealt with over the intermediate supports of an integral bridge. So another thing that the design basis section will look at is loads and load combinations. And again, this might seem sort of a little bit obvious, but it turns out that when you start talking about this, we all tend to consider temperature and soil pressures in different combinations depending on where you are. Not everyone considers temperature to be relevant to the ULS design, and a lot of regions will just look at the SLS combinations in terms of the temperature design. And that means that in order for an integral bridge design, because it's dependent on the overall expansion and contraction due to temperature, it then means that SLS will be the load combination that you design for. In the UK, we very much take the approach that the temperature forms part of the ULS combination, and ULS will tend to form a large part of our design. So again, it's highlighting how this is treated differently and what the key components are. It's also looking at the importance of the seismic combinations and how this adds additional considerations to your design. And this was primarily coming out of countries like New Zealand, Turkey, and some parts of the US, where obviously seismic actions are quite a lot more of concern than they are in places like the UK or Northern Europe. The idea is also to look at different analysis approaches. In the UK, we use the limit equilibrium approach. In other regions, you use a modified passive earth pressure derived based on the temperature movement. There's also some additional considerations when you go a little bit further north. For instance, Finland and other parts of Scandinavia have to deal with frozen soils, and those frozen soils then mean that different earth pressures are then mobilized when you are doing the design of the structures. And that adds an additional complication to doing integral bridge design. It also is one of the reasons why lengths of bridges are a little bit more limited as you go further north in Europe quite often, because the negative temperatures in the frozen soil lead to much higher earth pressures being applied to the structure or be mobilized by the structure as you get expansion into the frozen soil. So it's more sort of something that's applicable when you get into the ranges of sort of -20 and that sort of area. We're also looking a bit at sort of more detailed soil structure interaction. There's not going to be a huge section on this, but this is an approach where you go back to first principles and you look at the soil constituent models and look at non-linear soil properties, and you then carry out an analysis for the non-linear soil properties, which are then used to inform your design of the structure. Generally, this involves iteration between a structural analysis model and sort of geotechnical analysis program that does the sort of soil analysis. And it's generally quite an iterative approach in order to develop the earth pressure that you end up acting at the back of the abutment wall. There are some areas where it is beginning to be developed, sort of more detailed methods to soil structure interaction for shorter structures, sort of culverts, buried structures, things like that, but we're not yet doing it for sort of larger bridges, or at least I haven't heard of anything being done yet. Doing more detailed soil structure interaction is not permitted in all regions, and generally it requires quite a lot of calculation backup and references to sort of research material and sort of verifying the soil models in order to be able to use it, and that's fairly consistent across the world. So the final sort of one of the sort of penultimate section will be then dealing with the design approaches. We've sort of touched on this already, but it then looks at the imperial approaches that we use versus using more detailed modeling to develop the soil structure, interaction behavior between the sort of structure and the soil. It will look at the key aspects of different analysis models. What bits do we are particularly important when you develop an analysis model? How do you model the foundations? It will be slightly dependent on the prevalent ground conditions, but it's sort of try to put together some recommendations regarding springs, full pile models, sort of equivalent cantilevers, different ways of modeling foundations, and trying to pick up how that is done throughout the different regions as well. The final section of the document will then focus on common detailing practices and case studies. And this is probably one of the more interesting parts of the document, because it sort of highlights how much we actually have in common in how we do our detailing, but it also highlights how things are done a little bit differently. And it's been quite a useful learning experience to sort of look at other detailing practices, seeing what we can learn from how others are doing things, how we are doing things, and sort of sharing that knowledge to develop better and better details for integral bridge designs. This section will look at things like run-on slabs, which aren't terribly common in the UK due to maintenance issues that we've found with them, but they are commonly used in places like the US and most of mainland Europe. Also looking at different types of foundations. So for instance, H-piles tend to be very commonly used in the US, while in the UK we tend to use much more robust foundations, and there tends to be a mix of this depending on where you are. So again, it's capturing all those details together and putting together a bit of a discussion about which ones work well, how they work, and what you need to design for when you consider them. Also looking at joint connections at the road, asphaltic plug joints and other things, because again, this is quite a critical aspect of the integral bridge design, how you join it to the rest of the road and how you deal with the sort of maintenance part that goes together with that. And then it will look at typical connections between sort of the foundations and the abutments to deck, and as I mentioned earlier, the semi-integral bridges and the retrofitting details that are currently being developed by the French in particular. They seem to be sort of quite up on doing this sort of thing at the moment. So that's the main parts that are being developed under the working group 1.1.3 for the integral bridges. Thank you very much for listening to me.
I'd like to adjourn you about the work we are doing in the FIB on the topic of sustainability. We have a special activity group that has been established last year that started working on sustainability, along with a stable Commission 7, that is work sustainability since more than 15 years. So the commitment of FIB is high on this topic that is very, very important, very relevant, and model code as well deserved a relevant attention to this topic. And the commitment of FIB on this topic starts from the fact that many countries, including EU and other countries, aim to carbon neutrality by 2050. And so the world require a new generation of concrete structure, of sustainable concrete structure with minimal CO2 emissions, because concrete plays an important role in climate change. Climate change is a relevant part caused also by a concrete industry. So, as a structural engineer working with the concrete structures, we need to have this clear in our design choices and design strategies. So FIB wants to be prepared to lead the change into structural concrete community, and to drive a change of approach towards the design of concrete structure. Actually, construction materials have can plays a different role towards climate change phenomenon. And if we try to identify the amount of, if we try to quantify the amount of embodied energy and embodied CO2 that are strongly correlated in many cases, we can see that if we can quantify these quantities per mass, per volume of material, we can see that actually concrete perform very well, because the embodied energy per kilos and the embodied CO2 per kilos is one of the lowest embodied energy and embodied CO2 if compared with other materials that are typically used in construction industry, such as plastics and steel and others. But the amount of concrete that we use make concrete one of the most relevant industry within construction industry, the larger construction industry, causing CO2 emission and the emission of gases causing climate change. Because we use nearly 1 ton per year of cement per person worldwide, and cement is it's different years that we use this imagine to share with the community the importance of cement into this phenomena. Cement is the most used substances on the earth after the water. It can be estimated that the 50% in weight of whatever we produce in the world is made of concrete, for the amount and for the weight of concrete structure. And any alternative to concrete that we can imagine would not be scalable for the unavailability of alternative materials. So you can find many research activities at scientific and technical literature dealing with geopolymers. Geopolymers can be very good alternatives, probably perform better in terms of CO2 emission, but it cannot be used as a real alternative because cannot be scaled up to the amount of cement that we use for concrete structure in our industry yearly. But we need to identify strategies to reduce the emission caused by concrete industry. And then I want to share with you this graph that has been produced by Global Cement and Concrete Association. You can see the CO2 emission caused by concrete, and on the top of the curve you can see the expected increase of the CO2 emission from 2020 up to 2050. You can see that it's going to be more and more. That's why this is because the amount of concrete structure that we expect to produce yearly will increase year by year, driven by the request of the developing countries. And then we need to identify possible strategies to reduce the CO2 emissions. And we can identify different strategies that likely could be stressed to reduce this amount and to get the target of zero emission by 2050. And we can see that efficiency in design and construction, efficiency in concrete production, and saving in cement and binders plays an important role into this strategy that is here proposed. So the role that structural designer can play towards this objective is important, and we need to get the awareness of this role. and to use this awareness into the strategies that we adopt day by day when we design reinforced concrete structure. But then, very practically, we can deal with 4 directions for reducing CO2 emission, and we can manage this objective. One, the first direction is dealing with alternative binders to normal cement, dealing with binders that can present and different strategies in scientific and technical literature are being investigated and can be adopted now and will be available in the future as alternative to normal cement. But anyway, many of these are still cement based. Then the second direction we can identify is dealing with new mix design to reduce the amount of cement, dealing with admixtures and with new recipes to produce concrete that can exhibit the requested mechanical and physical performance that we need in our design, but with a reduced amount of the binder of the cement. And then the third direction is optimizing structures. We can try to work on the amount of reinforced concrete that we can use in our structure. And so new methodologies, more sophisticated design procedures, and more sophisticated models can support us to optimize the structure, and so to have equivalent performance, the same performance for the wall structural systems with reduced amount of reinforced concrete. And then the awareness is the fourth direction. We need to quantify the amount of the environmental impact, the amount of CO2 emission that we are causing with any single structural project, because we need to manage this number on our desk. We need to manage these numbers so to deal with the alternatives, to identify and assess the different alternatives that we can imagine into the structural design of any single structure. So the SAG Sustainable Initiative, even if Commission 7 was still active and is a stable commission in FIB decided to trigger a new initiative. SAG stays for, is the acronym of Special Activity Group on Sustainability. We started this new activity with 3 clear objectives. We want to communicate and to enlarge the awareness of the environmental impact that reinforced concrete structure and the design of reinforced concrete structure cause in terms of CO2 emission. And we want that the community of the designers enlarge their awareness about this, are made able to quantify and to manage this aspect into their design. So we have 3 clear objectives: a comprehensive database of the environmental impact of concrete structure and concrete components and structural systems related to concrete structure. Then we want to propose a reliable and feasible methodological approach to support designers to quantify the environmental impact of a concrete structure into their single projects. And then we want to support the designers with tools and knowledge and benchmarks to guide the decision-making process of any single project towards optimal structural solution, and so the optimization of the environmental impact of any single design. Practically, we expect to have 3 main outcomes. We want to propose a platform for the environmental impact inventory data of reinforced concrete elements and components and systems, to make it available for the members of our community to let them investigate and quantify the environmental impact of their design. Then we want to produce a report on the methodology to support designers dealing with this kind of calculation, and possibly this can be in a sort of product category rule for structural concrete. Who is familiar with this matter, with the ISO 14000, understand what is a product category rule. Is a sort of guideline to support the quantification of the environmental impact for any industrial product, and we would like to deal with this with the product reinforced concrete structure. And then we expect to have a report on optimization strategies and best practices on this topic. The target audience of our SAG is clearly designers, but also policymakers and society in general. Then we have arranged our work into two task groups. The first one deals with the database, the prioritization of data, and to the development of the data platform that is expected to be continuously maintained and continuously updated with data coming from the different regions of the world, because we know very clearly, and this is very evident, that environmental impact depends on the area where we are dealing with the construction. And so we need the help of the local FIB groups to maintain the data of the platform. And so I encourage you to engage into this activity also to support our activities for your country. And then this is the structure of the platform we expect to set up. A platform of CO2 inventory data for concrete structure that communicates with suppliers, designers, is updated with the data coming from different stakeholders, builders, owners, and then you can see EC3, EcoInvent, that are databases that are typically used by LCA community, the community that deals with the environmental impact calculation of industrial processes. And then we want to collaborate. We are still collaborating with other organizations like FIB, working on the same topic. And then the second task group, whose objective is the identification of best practice and optimal structural solution. So to share with the community opportunities, pros and cons of the different approaches, the novelties into technological novelties, but also methodological novelties for managing environmental impact quantification into the structural design processes. This topic is high risk, high gain, because we are aware that we are dealing with a matter that is really complex and complicated, and that our community is not familiar with these topics, but we imagine that this work can be fruitful, because we imagine that our community will be reactive on this topic. So we have a workflow that would expect by into the next 2 years to get the outcomes I have described, and then for the data platform, start with a continuous updating of the data. And then, as a final word, few information about COM7 task groups. We have the COM7 is dedicated into this scenario to the vertical dealing of specific topics. And so we have now 5 task groups active on working on general framework of sustainable concrete structures, the environmental product declaration for the concrete products, resilient concrete structures, and then sustainable concrete masonry components, and then the management of waste materials and industrial byproducts for high performance concrete structure. So thank you for your attention, and I really hope that you can engage into this activity and contribute from fibUK with your passion and with your work on this topic. Thank you very much.
I just give a small clarification. We're talking about Model Code 2020. The 2020 refers to, it's a sort of timestamp on the technology that the code is based upon, not the publication date. Anyway, I'd like to recognize and give thanks to two of my colleagues who were involved in the management of Task Group 10.1. Agnieszka Biga, who was the deputy convener, and Gary Dieterin, who was the technical secretary of that group. And they've worked very assiduously over a period now of, 24, so 8-9 years. So let's get underway. What I'm going to talk about today, I'm going to give you a brief insight into the historic development of the FIB Model Code, outline the conceptual scope of Model Code 2020, and overview its contents, and then talk a little bit about the philosophical basis for the code, i.e. that it's a sustainability-driven, performance-based approach to design, execution, and lifecycle management of concrete structures. And then I'll touch upon some facets which are dealt with in the code, such as improved materials and mechanical performance models and verification processes, models and guidance for various deterioration processes that need to be addressed, particularly for existing structures, and then existing structures, models for the assessment of actual or enhanced diminished structural capacity, and the role of monitoring and the value of information in life cycle management of these structures. And of course, with existing structures, we must recognize the need for interventions upon structures, and I'll finish with some concluding comments. But to start with, I'd like to emphasize that the engineering core and technical processes of Model Code 2020 still utilize familiar design approaches such as limit states or limit values, which are associated with reliability thresholds, taking into account relevant reference periods. So moving on to the evolution of the FIB model codes, there have been 4 up to the current time: 1970, 1978, 1990, and the last one, Model Code 2010. These codes have contributed over a wide range of years to the development of the SEN code, EN 1992, but also have influenced the development of Asian and African model codes. But the project I'm talking about tonight, Model Code 2020, this is the first time that significant provisions have been included for dealing with existing structures. And the graphic pictures on the right there, on the right-hand side is Model Code 2010, which is a hardback volume. And then on the left, that's a galley proof for Model Code 2020 used in the checking process for the preparation. Model Code 2020 deals with new, existing, altered, adapted structures, which includes retrofitting new structural elements in parts of existing structures, interventions for various reasons, strengthening, extension of life, and so on. But of course, a critical element of this is the performance-based approach. And we hope that this will facilitate usage of new and evolving materials or technologies and lead to greater material and structural efficiencies in time. Our starting point, as you might expect, was the previous code, Model Code 2010. That was prepared in 5 number parts, comprising 10 chapters and about 430 pages. Model Code 2020 is in 10 parts, 39 chapters, and is in the order of about 800 pages. So it has a greatly extended technical scope and coverage. Of course, it deals with new build as did Model Code 2010, but there's considerable growth in its content to deal with existing structures and their management and interventions upon them. And of course, the new code takes into account technical developments which have occurred since the preparation of Model Code 2010. And there's additional things such as expanded reference lists and related factors. But what I'd like to point out is that supporting FIB bulletins and technical papers have been prepared, which provide additional information so that it's helped reduce the page count in the code, but provides useful additional insight into the code and the operation of the philosophy. So on to the table of contents. Part 1 deals with scope and terminology in chapters 1 and 2. Part 2 deals with basic principles. So this comprises chapters 3 to 10. It outlines the sustainability perspective and the performance-based approaches adopted in the code, sets down the principles of lifecycle management and of quality and information management adopted for the code, as well as principles of execution, conservation, and circularity and dismantlement, as well as the implementation of quality and information management for or during the lifecycle management of existing structures. Part 3 deals with the principles of structural verification in chapters 11 and 12. So this deals with structural performance evaluation and the principles of structural design and assessment. Moving on, part 4 deals with actions on structure. So that's a new component in the code relative to Model Code 2010. Part 5, input data for materials. This comprises chapters 14 to 19, which deals with concretes, reinforcing steel, pre-stressing steel and pre-stressing systems, non-metallic reinforcement, fibre reinforced concrete, as well as materials and systems for protection, repair and upgrading. Obviously, these are required particularly for existing structures, but may also be incorporated in the design of a new structure. Part 6 deals with input data for interfaces. As we have more materials, we have more interfaces than Model Code 2010. And this part deals with or comprises chapters 20 to 25, bond of embedded steel reinforcement, so anchorages and laps, bond of embedded non-metallic reinforcements, bond of externally applied reinforcement, as well as new concrete being applied on top of existing concrete or old concrete. Concrete to steel, so the steel in this aspect is structural steel sections where the bond is achieved by mechanical interlock, and chapter 25 deals with anchorages in concrete. In part 7, design and assessment procedures, we come to the main technical content of the code. So there are, this comprises chapters 26 to 34, sets down the conceptual approach to design and assessment, as well as the detailed approaches to design and to assessment. Chapter 29 is concerned with structural analysis and dimensioning. And chapter 30 concerns evaluations, which is a different word, which means really verifications of structural performance. So this is a very major component of the code and a very large proportion of the code document. Chapters 31 deals with evaluation of other aspects of social performance, which I'll come back to in a moment. And 32, evaluation of environmental performance. So this comes back to and uses tools such as life cycle assessment and evaluation of economic performance, linking to life cycle costs. And chapter 34, it's very significant, important chapters dealing with sustainable decision making. Part 8, execution, chapters 35 to 37 deals with execution management, construction works, and of course, execution of interventions, which may be for extension of life, upgrading, or the like. Part 9 deals with conservation, which is another term for life cycle management, and part 10 deals with circularity, dismantlement and reuse. The model code, draft model code 2020, was formally approved by the vote of the FIB General Assembly at its meeting in Istanbul on the 4th of June last year. And since then, we've been busy preparing a publication version of the code, which has involved the FIB Secretariat and the Model Code 2020 Secretariat. And I'm pleased to be able to say that a hardback version of Model Code 2020 should be available in April 2024. So not long now. This achievement has been a truly global effort. We've had apparently more than 1,400 people from 67 countries involved in various ways, such as being authors, reviewers, or making a variety of other contributions over the time which has taken us to develop the code. And of course, we've been very grateful for the support of FIB's 40 national member groups in this work. So I've said that Model Code 2020 adopts a sustainability-driven, performance-based approach to design, execution and lifecycle management of concrete structures. Of course, this relates back to the three pillars of sustainability: the social pillar, the environmental pillar, and the economic pillar. And what Model Code 2020 seeks to achieve is the ability to design structures achieving a satisfactory balance between the influences and requirements of these different pillars. What I perhaps need to draw to your attention is how the social pillar has been divided into two aspects: structural aspects, so that's structural safety and related functional performances. So these are the conventional engineering issues that we're used to designing for, but also in terms of the wider application of the social pillar, there's non-structural aspects such as health and quality of the built environment, security and safety, so non-structural safety related aspects, so the wider elements of a project, and also things like aesthetics and cultural heritage, as well as impact on the local community. But there may be other facets for other particular projects. So we've heard from the previous speaker about the need to reduce the embodied carbon footprint of construction, release less CO2 to the atmosphere. So we need new thinking is being developed, and processes are changing. The graphic here on the left, on the vertical axis, shows the CO2 reduction potential in various phases of the project. So the horizontal axis concerns planning of a project, the design, its building, and its operating. So you can see through the life of the project the potential for reduction of CO2 or effects upon the environment reduce. In the context of CO2 emissions, I think it's important to recognise that about 40% of those arise from buildings and constructed assets. So if we look at this graphic, so you could, of course, build nothing or as little as possible, and maybe try and solve the operational requirements, the needs in a different way to building. But of course, a good reduction in carbon footprint of construction can be achieved by repurposing and renovating existing buildings rather than demolishing and building anew. And I have a case history here which is concerned with the renovation of the United Nations New York City headquarters campus. And this study looked at the carbon saving benefits of retrofitting and renovation versus demolition and new build. The idea was to try and find out which approach is best. And it was found that it would take something like 35 to 70 years to offset the initial outlays of embodied carbon if the existing UN campus were demolished and reconstructed. And that estimate took account of the operational efficiencies which would have been gained from new construction, new materials and so on. So obviously the study shows a strong case for retrofits and renovation of existing building stock rather than the demolition and new build approach. In terms of adaptations of existing assets, I found 2 examples of the conversion of grain silos into other usage. Now, you'd think a grain silo was a pretty tough project to take on to adapt to something else, but these are rather interesting. In Oslo, they converted the grain silo in the port into student housing, as is shown here in the various photographs. And a similar project, but very prestigious project in the port area of Cape Town, the existing grain silos, which are shown here as the concrete elements in the picture, were converted into 2 entities. One is the Zeitz Museum of Contemporary Art Africa, known as the MOCA, and then also a 5-star silo hotel. You can see, well, you can't see the conversions that were made within the concrete silos, but you will see though that there was other works done in terms of new construction elements which complemented the adaptation of the existing silos. So those elements are built above the existing structure. Very interesting project, very central to the redevelopment of those areas of the port. Now, why is a performance-based approach to sustainable design, execution and lifecycle management important? Well, I think we probably all appreciate our world is changing greatly and increasingly quickly, so we urgently need to do things differently. And it's hoped that a performance-based approach can help remove barriers to the necessary and rapid changes in various forms of technology that we use in construction. And this will facilitate the uptake of these new changed technologies and hopefully lead to reduced embodied carbon and reduction in the footprints that the construction industry has and its release of CO2 into the atmosphere. And the pictures below on the left-hand side that's the Pantheon, and there's various other pictures from places around the world with some various forms of advanced materials, new forms of construction. And FIB has taken steps towards this goal of a performance-based approach within Model Code 2020, and I'll explain a little bit more about that in a moment. But FIB needs to continue and expand its efforts to move its sustainability agenda forward and realise its vision of a future construction industry creating low carbon, high performing, durable concrete structures, as you've heard from the previous speaker. Now, in terms of performance-based approach, I'll give you a simplified illustrative example. In this example, we're considering 4 tiers. So the top tier would be the owners and users' higher level performance or outcomes-based requirements. So these are societal and functional requirements. Tier 2, undertaken by technical consultants, engineers, other professionals, will turn the Tier 1 requirements into strategies and engineering technical performance specifications, which are then used at the Tier 3 level by contractors and constructors to employ appropriate performance-based specifications for materials and manufactured systems. And then Tier 4, in this example, the material suppliers and manufacturers would use, again, a performance-based specifications to provide suitable materials and systems, but that would be linked to appropriate test procedures to demonstrate that performance specifications are met with an appropriate degree of reliability. So what are the higher level performance requirements? Well, clearly human environmental safety and risks are pretty significant, pretty important. Think factors like the design service life, the working life, the functionality, the key performance metrics for the entity which is to be constructed, durability, longevity, the prospects of deterioration, what the serviceability limits are, the operational aspects, how they need to be defined, robustness and seeking to limit vulnerabilities, resilience of functionality of the entity, the bridge, the rail system, the dam, etc., which may be being created. And of course, there are other aspects of functionality, perhaps adaptability, appearance, impact on the local community, heritage, and a significant factor in this changing more extreme world is the tolerability of damage during extreme events and maintaining functionality, as well as life cycle costs and revenues and life cycle impacts. And of course, all of those things lead to specific design and process considerations, key performance metrics for the project under consideration. So those tiers on the left-hand side, those factors are shown on the left-hand side here under tier 1, but indicative tier 2 engineering and technical performance requirements, these are the ones that we are used to working with. So target reliability levels, say for ultimate limit state, serviceability limit state, condition limit states, consequence class, design life of the structure and components, and how the service life design is going to be developed, the strategy and the planning required, how the structure will be managed through its life cycle management, what hazards and vulnerability issues need to be taken into account, how resilient does the structure need to be to specific incident scenarios, and what the requirements might be for service and environmental changes through the life of the structure. And of course, again, costs and environmental impacts. And we've developed flowcharts which represent these processes. They're quite complicated. But if we take a simplified performance-based model approach, we've got the blue box at the top there, the sustainability-orientated performance requirements. The yellow box at the bottom shows the performance evaluation, the verification, and then in the middle, the conceptual design or redesign adaptation approaches employed, as well as life cycle management, so the activities and intervention processes which may be required. So they are incorporated into this flowchart, which shows the interactions, the different levels of the tiers and the way things work. But I don't have time to go into that today. But if we step back to the simplified performance model that I explained before, the processes in the flowchart I've just put up essentially come down to those elements of the activities which define the performance-based requirements. So the purple area at the top, and the performance verification activities in the red zone below. But of course, there's also these other activities, these technical processes for the design of new structures and the adaptation, upgrading, lifecycle management of existing structures there in the middle, which I outlined before. So moving on, I'll just highlight some of the developments within the code. There are improved material and mechanical models. These apply to new construction and to existing concrete structures, and they may be particularly beneficial for circumstances relating to long life or existing structures, which of course do suffer from deterioration. And a classic representation of these situations is shown here, graphic on the right. The vertical axis relates to performance and the horizontal axis relates to time. So the blue line, dashed blue line there, which falls with time, representing deterioration effects. So the capacity is reducing with time. The red dashed line marked S is the load effect, and that's shown to increase with time for increasing load. But of course, that load may remain constant, so the line would then be horizontal. But of course, there are aspects of the resistance effects which may not be taken into account during design, such as compressive membrane action, perhaps increase in strength in the concrete with time, and that may justify an extension of the service life of the structure. And I'd just like to draw attention to the fact that the code incorporates for performance evaluation a variety of methods and levels of techniques in the levels of approximation or levels of verification employed in the design of new structures, but particularly for the assessment of structural assessment of existing structures. So in this example here, it defines 6 levels of potential assessment or verification. So this is broken down into qualitative and quantitative assessment processes, those which are measurement-based and those which are model-based. I don't have time to go into these, but it does provide a very wide range of different procedures which can be applied. And just going to touch upon some other developments. So for existing structures, there's a need to model deterioration processes. Unfortunately, currently, the consensus models for initiation and propagation are really restricted to the corrosion of steel and the effects upon concrete arising from that. So these involve both material models and structural models to make an assessment of the changes in capacity. But it's fair to say that future work is envisaged on the initiation and propagation of a much wider range of concrete deterioration processes. But we didn't have time to develop that in the current cycle. Lifecycle management, that recognises the role of monitoring and the value of information gained from that, which helps improve the quality and safety of the constructed assets. Again, it's a basis of that information helping justify extended useful life. It clearly provides diagnostics and assists in, say, infrastructure risk assessment and management. And maybe at some future time, we'll be able to monitor safety in more reasonably real time. And of course, with existing structures, there's a significant contribution in the code about undertaking interventions upon structures. So of course, you need to identify the deterioration of damage mechanisms which are in play, and then evaluate the potential intervention options, select remedies and repair strategies. And what's incorporated in the Model Code 2020 aligns with the treatment set down in ISO 16311, maintenance and repair of concrete structures, as that provides a useful framework to refer to and is being further developed by ISO and saves a lot of content being incorporated into the code. So there's been a principle of refer out whenever possible rather than redevelop. So coming to my concluding comments, Model Code 2020 provides improved technical guidance for the design of new structures, as well as the assessment, adaptation, and conservation of existing structures. I'd like to reassure you that Model Code 2020 uses engineering processes and verification procedures or validation procedures, which we're familiar with, limit states, limit values for ULS, SLS, with associated reliability and relevant reference periods. And what we're seeking is that these capabilities will be helpful or maybe critical to extending the useful life of concrete structures and or upgrading them to satisfy existing or revised, often increased performance requirements, so that we can help diminish the need to demolish structures, we can adapt them, people will have better tools for doing those things. I'd also point out that the performance-based framework incorporated in Model Code 2020, we studied the variance on these approaches used currently in international and national construction contracts. So they're grounded in reality, but I would say that more work is needed to develop and extend the use of these methodologies. So it's a work in progress for FIB and other bodies. But of course, the ultimate goal of the new version of the model code is that it's going to be better suited to the future demands and the circumstances we're going to encounter in the years ahead. And there are technical papers and PowerPoint presentations and various things available on the FIB International website, which gives further information on Model Code 2020. And that brings me to an end.